Hey there, fellow science enthusiasts! Today, we're diving into the fascinating world of statistics and biology. Now, I know what you might be thinking. Statistics? Isn't that all about boring numbers and complex formulas? But trust me, statistics are a biologist's secret weapon. Think about it. Biology is all about studying living things, and living things are full of variation. From the size of leaves on a tree to the population of penguins in Antarctica, there's variability everywhere. That's where statistics come in handy. They give us the tools to make sense of all this variation, to see the patterns hidden within the chaos. Statistics help us design better experiments, analyze data effectively, and draw meaningful conclusions. Whether you're investigating the effectiveness of a new drug or tracking the migration patterns of monarch butterflies, a solid understanding of statistics is essential. So, buckle up and get ready to unlock the power of statistics in biology. Let's kick things off with the basics. Descriptive statistics. Imagine you've just collected a bunch of data from your latest experiment. You've got numbers everywhere. Before you can even begin to understand what your data is telling you, you need a way to summarize and describe it. That's where descriptive statistics come in. Descriptive statistics are like the paintbrushes in a scientist's toolkit. They help us paint a clear picture of our data using numbers. Two key concepts in descriptive statistics are measures of central tendency and measures of dispersion. Measures of central tendency, like the mean, median, and mode, tell us where the center of our data lies. Think of it like finding the bullseye of your data. The mean is the average of all the values. The median is the middle value when the data is ordered, and the mode is the most frequent value. Measures of dispersion, such as the range, variance, and standard deviation, tell us how spread out our data is. A narrow range means the data points are clustered closely together, while a wider range indicates more variability. By using these simple yet powerful tools, we can start to make sense of our data and uncover the stories hidden within. Now, before we even think about collecting data, we need to make sure our experiments are designed to give us reliable and meaningful results. This is where experimental design comes in. A well-designed experiment is like a well-built house. It has a strong foundation and all the necessary components to support our scientific investigation. One crucial aspect of experimental design is having a clear research question. What exactly are we trying to find out? Once we know what we're looking for, we can determine the best way to collect the data we need. This involves identifying our variables, the factors that can change in our experiment. We also need to consider factors like sample size. How many individuals or samples do we need to study to get statistically significant results? Randomization is another important concept. It helps ensure that our groups are as similar as possible, minimizing bias and increasing the reliability of our findings. By carefully planning our experiments and considering these key principles, we set the stage for robust and trustworthy data analysis. Imagine you're trying to estimate the average height of all sunflowers in a field. You wouldn't measure every single sunflower, would you? That would take forever. Instead, you might measure a sample of sunflowers and use that data to estimate the average height of all sunflowers in the field. This is where confidence intervals come in. A confidence interval gives us a range of values within which we are confident the true population parameter lies. It's like saying, we're 95% confident that the average height of all sunflowers in this field is between 4 and 6 feet tall. The width of the confidence interval tells us how precise our estimate is. A narrow confidence interval indicates a more precise estimate, while a wider interval suggests more uncertainty. Confidence intervals are essential tools for understanding the reliability of our estimates and drawing meaningful conclusions from our data. Hypothesis. Testing, unveiling the truth in data. Have you ever wondered if a new fertilizer really makes plants grow taller, or if a certain drug is truly effective in treating a disease? This is where hypothesis testing comes in, one of the cornerstones of statistical inference. Hypothesis testing is like playing a game of scientific prove it. We start with a null hypothesis, which is a statement that there is no effect or difference. For example, our null hypothesis might be that the new fertilizer has no effect on plant growth. Our goal is to see if we have enough evidence to reject this null hypothesis. We do this by collecting data and calculating a p-value. The p-value tells us the probability of observing our results, or even more extreme results, if the null hypothesis were actually true. If the p-value is small, typically less than 0.05, we reject the null hypothesis and conclude that there is evidence to support our alternative hypothesis, that the fertilizer does indeed affect plant growth. Hypothesis testing allows us to make objective decisions based on data and draw meaningful conclusions about the world around us. Regression analysis, unveiling relationships in data. The world is full of relationships between the amount of sunlight a plant receives and its height, or between the number of hours a student studies and their exam scores. Regression analysis helps us uncover these relationships and quantify them. Think of regression analysis as a way to find the best-fitting line through a scatter plot of data points. This line, called the regression line, helps us understand how one variable changes in relation to another. For example, we could use regression analysis to investigate the relationship between the age of a tree and its diameter. By plotting the data points for age and diameter and fitting a regression line, we can estimate the average increase in diameter for each year of growth. Regression analysis is a powerful tool for understanding and predicting relationships between variables, providing valuable insights in various biological contexts. ANOVA comparing multiple groups. Often in biology, we want to compare more than two groups. For example, we might want to compare the effectiveness of 3 different types of fertilizer on plant growth. This is where ANOVA, or analysis of variance, comes in handy. ANOVA is a statistical test that allows us to compare the means of multiple groups simultaneously. It helps us determine if there are any significant differences between the groups, or if the observed differences are simply due to random chance. Imagine we conduct an experiment to compare the effects of 3 different exercise regimens on weight loss. ANOVA can tell us if there's a significant difference in average weight loss between the groups following each regimen. If the ANOVA test reveals a significant difference, we can then perform further analyses to determine which specific groups differ from each other. ANOVA is a valuable tool for comparing multiple groups and identifying significant differences, enabling researchers to make informed conclusions about the factors influencing their study subjects. Data visualization, making data speak visually. They say a picture is worth 1,000 words, and that's especially true when it comes to data. Data visualization is the art of turning raw data into meaningful and visually appealing representations, making it easier to understand patterns, trends, and outliers. From simple bar charts and line graphs to more complex heat maps and 3-dimensional plots, there's a wide range of visualization techniques at our disposal. Choosing the right visualization method depends on the type of data we have and the message we want to convey. For example, a line graph might be ideal for showing changes in population size over time, while a scatter plot could be used to illustrate the relationship between 2 variables like temperature and enzyme activity. Data visualization is about more than just making things look pretty. It's about communicating complex information clearly and effectively, enabling us to grasp the story our data is telling us. Handling large data sets and advanced techniques. As technology advances, we're now able to collect and store vast amounts of biological data. This presents both exciting opportunities and analytical challenges. Handling large data sets requires specialized tools and techniques to manage, process, and extract meaningful insights. Statistical software packages like R and Python have become invaluable for analyzing large data sets, providing a wide array of statistical functions and data manipulation capabilities. These tools allow us to perform complex analyses, build predictive models, and uncover hidden patterns within massive data sets. Moreover, advanced statistical techniques like machine learning are gaining traction in biological research. Machine learning algorithms can sift through mountains of data, identify complex relationships, and make predictions with remarkable accuracy. While these advanced techniques may seem daunting at first, numerous resources and online courses can help biologists develop the skills needed to navigate the world of big data and unlock the secrets